Okay, so first, fluctuations are correlated on scales that are super Hubble at decoupling. This is one of the main reasons for which we trust inflation as a good paradigm for the generation of fluctuation. So how can we see it? We can see it first in the temperature spectrum, because on the larger scale, smallest multiples, you see the famous Sachs-Fault plateau. The Sachs-Fault plateau is an indication that at the time of decoupling, fluctuations were correlated on super Hubble scales. And for this, you need, of course, a mechanism like inflation that solves the horizon problem in the way you know. Temperature is not the most robust indication, because you could generate this plateau in temperature on low scales with the integrated Sachs-Fault effect. It means that you could generate this correlation in the temperature fluctuation after decoupling without invoking any horizon bigger than the Hubble scale. And in fact, it works in this way in the mechanism with topological defects. But what is very robust is that when we correlate temperature and polarization, we see on small scales a correlation. And since polarization cannot be generated by the integrated Sachs-Fault effect, the first multiple in the TE correlation spectrum are really a proof that at the time of decoupling, fluctuations were correlated above the Hubble scale. So the causal horizon must be bigger than the Hubble scale, and this calls for inflation. Then there is the fact that we see the acoustic peaks. So the acoustic oscillations are coherent, meaning that when a given Fourier mode enters the horizon, all the modes start to oscillate in phase. Will not be the case with other mechanisms. Fluctuations seem to be nearly Gaussian. This is what Planck indicates. And this is a natural prediction of all simple inflationary models. Then the peak location seen not just by Planck, but by previous experiments is an indication that fluctuations are mainly adiabatic. We will talk later about a possible small amount of isocurvature mode. This is also a prediction of single field inflation. And finally, at leading order, we see that the primordial spectrum is close to scale invariant. So these are the basic predictions of inflation, which are validated, not just with Planck, but with previous experiments. So now, what more can we say with Planck? First, I must recall you that in single field slow roll inflation, the shape of the inflaton potential maps into a primordial spectrum of scalar and tensor fluctuations. In particular, the slope of the inflaton potential around a given scale will produce a scalar and tensor perturbation at another given scale in Fourier space. So in the plot, you see the inflaton potential in a small region around a value that we call phi star. Phi star is supposed to be the value of the inflaton when typical cosmological scales become larger than the Hubble scale during inflation. So the properties of the potential in the vicinity of phi star will explain the property of the scalar and tensor spectrum around a given pivot scale k star. In the scalar fluctuation that we call here AS, also called very often the curvature perturbation, the amplitude around a given scale is given by this strange combination v to the 3 over v prime, which is not so difficult to prove. The slope, the tilt, is related to v prime over v square, v second over v. These are called the two slow roll parameters, because if inflation is in slow roll, meaning just if the Hubble scale is varying slowly during inflation, or the potential v is varying slowly during inflation, then we can do a slow roll expansion in parameters that are smaller and smaller at the next order. So the first two orders are this v prime over v square, v second over v. If we wanted to compute the dependence of the tilt over the scale, called the running, we will need one more parameter, v to the 3 over v, as well as the square of the previous parameter. But at any new order, things are smaller and smaller. This is why in single field slow roll inflation, we predict almost scale invariant fluctuation with a sizable tilt, with a suppressed running, and even more suppressed running of the running, etc. And the situation is the same with the tensor spectrum or gravitational spectrum that you see on the right. Their amplitude is governed by V, the value of the potential during inflation, the tilt by the first slow roll parameter, etc., etc. So the slow roll expansion is defined in the way we said. And you see that if we want to measure, to know everything about the inflaton potential in a given region, we need to measure the shape of the scalar potential of the, scalar spectrum over a range of wave number of k modes. This will give us a strong indication, but you see that on the left, all the formulas depend on ratio of V prime over V, V secant over V. So the knowledge, even very precise, of the scalar spectrum is not sufficient. In order to remove the degeneracy, we must fix the absolute scale of V at a given k. And for this, we would need the tensor spectrum. As long as we don't measure tensors, but we only get a bound on the tensors, there will still be a remaining degeneracy, and even a perfect knowledge of the scalar spectrum will give us a family of inflationary model, but not a definite value of and shape of the inflaton potential. Okay, so now the scalar spectrum maps onto the CMB temperature spectrum. It's not a trivial mapping. If it was a trivial mapping, any value of k in the scalar spectrum would give you a multiple L in the temperature spectrum. It would be a one-to-one mapping. It's not exactly like this. It's explained on the graph. We see the last scattering surface. It's a sphere around us. Under a given angle theta, we see a given scale on the last scattering surface, and this scale can be put in correspondence with Fourier modes of fluctuations on the last scattering surface. In the graph, you see that you put it in correspondence with a wavelength given by the scale factor A at decoupling times the co-moving wavelength pi over k, where k are the wave numbers that we saw before in the primordial spectrum. So this would give you a relation, theta times the angular diameter to decoupling would be equal to the scale factor at decoupling times pi over k. And since pi, the angle theta is inversely proportional to the L of the multiple CL, this would give a one-to-one correspondence between a given value of L and a given value of K. However, under the angle theta, we also get a contribution from other wavelengths. Here you see we get a contribution from a wavelength which is neither orthogonal, neither aligned with a line of sight. So we get on the same angle theta a contribution for a mode with a smaller wavelength. And we could go on with modes which are almost aligned with a line of sight. And in this case, an even smaller wavelength contribute to the same angle. So it means that a given C of L gets a contribution for a range of wave numbers k and not only from one wave number. This is why when we try to measure the primordial spectrum through the CMB, we have to keep in mind that the CMB comes from the primordial spectrum convolved with some kernel, which is in fact given by spherical Bessel function. Okay, with this very, very summarized theoretical input, we can go on. We are going now to look at the Planck constraints. And we start by looking at the reconstruction of the scalar spectrum, which maps onto the CMB temperature spectrum in the way we say it. And I forgot to say that the primordial spectrum also maps on the CMB polarization spectrum, the E polarization, which has been already well measured by WMAP, and we don't know yet the results from Planck. There is also a mapping here with a different kernel, a different Bessel function, so that the two, temperature and polarization, bring us independent information on the primordial spectrum. Now the tensor mode. The tensor mode also contributes to the temperature and polarization spectrum. For the temperature, the tensor mode will only contribute to the first multiples. They are suppressed at high L, and we don't have time to say why. It has to do with the fact that tensor modes are seen mainly through the integrated Sachs-Rolle detector. So if we look at the full tensor spectrum, at the full temperature spectrum, what we see comes from scalar and tensor contributions. And because the tensor contribute to the large scales and not to the small scale, the tensor will appear as a deficit of the small scale temperature relative to the large scale temperature. It's the same for the e-polarization spectrum, while for B mode are seeded at the primordial level only by tensors. So B mode would be a distinct signature of B modes of the gravitational waves generated during inflation. But B modes are very difficult to measure, much more than E modes, because they are small. Even if inflation takes place at the gut scale, which is the maximum scale allowed, and B modes are then maximal, even in this case, the tensors will contribute to B mode with a smaller amplitude than E modes. As you can see in this plot, this is the maximum B mode we could expect given W map. So this is a level already ruled out by Planck, while the green would be the E mode. So now here is a Planck temperature spectrum on the top. On the top you see the data points. The little gray point are the raw data, the blue are the bin data. The red is the best fit lambda CDM model, which is based on a power law primordial spectrum, a tilt, and no tensors. And in the bottom, you see the residual. So you see the data points divided by the best fitting lambda CDM model. In this model, the tilt is equal to 0.96 with a small error bar. What is striking is that now, the case of a Harrison-Zeldovich spectrum with a tilt equal to 1 is 5 sigma away from the best fit. So Planck is really proving in a consistent and in a robust way that the tilt is smaller than 1. And this is a more robust conclusion than with WMAP because it remains true even when you take extended models. And this is what we show on the next slide. So there are many plots on the next slide. Just look at a few of them. This row here shows the constraint on NS together with another parameter in various extensions of lambda CDM. The first column is lambda CDM plus a free W equation of state parameter of dark energy. Then the next column is is lambda CDM plus running, a tensor contribution with R, which is a tensor to scalar ratio. The next column is lambda CDM plus running. Then lambda CDM plus a free primordial abundance of helium instead of taking the BBN prediction. The next one is with a free density of radiation, assuming that radiation particles could be different from the usual photons and 3 active neutrinos. Then adding a neutrino mass and then adding spatial curvature. So if we look now at the interesting row, NS with one of these 3 parameters, the first green line corresponds to NS 0.96, the lower line corresponds to NS of 1. You see that in all these cases, we remain far from NS equal 1, except when we take a free helium fraction and free NF, and in this case, we can marginally touch NS equal 1 at the 2 sigma level. So the conclusion is that the fact that NS is smaller than 1 is now robust. While with WMAP was favoring NS smaller than 1, but with extended cosmology, it was very easy to have NS equal 1, fitting the data very well. Let's zoom on this case with free NS and free running. This is the purpose of the next plot. You have here the constraint on running versus NS in an extended lambda CDM model. In red, you take the information from Planck. You take the first multiples of WMAP for polarization. This is useful in order to constrain rayonization. And rayonization is slightly degenerate with the T. So it makes sense to take a few multiples from WMAP polarization. So in the red, you have Planck, you have WMAP polarization, you have baryonic acoustic oscillations measured by large-scale structure. And in the blue, it's the same, but without the running. So you see that with running, we have a slightly larger constraint on the primordial tilt, but not so much larger. Sorry, the blue is without the tensors. The running is present in both cases. The red is with tensors and the blue is without tensors. In both cases, you see that a slightly negative value of the running is preferred, but only say at the 1 sigma level. So it's not significant at all. In both cases, at the 2 sigma level, everything is compatible with no running. And this is what we would expect from a single field inflationary model, because in single field inflation, in slow roll, unless you are marginally deviating from slow roll, but this would be rather unnatural, the running is predicted only at second order in slow roll, which means that it is naturally suppressed. And indeed, the magenta curve here, or purple curve, call it in whatever way, the purple curve shows a typical order of magnitude that you expect for running in single field slow roll inflation. It's not exactly 0, but it's typically much smaller than the value of minus 0.02 or 0.03 that you see in the graph. So we don't need to invoke running, and so we don't rule out the simplest model of single field slow roll inflation. So now let's assume that we live with single field slow roll inflation with this prior. We will leave for the end of the presentation the more complicated possibility to have features in the primordial spectrum or to have isocurvature. We leave this for the next slide. We focus on single field inflation, slow roll prior, and we try to fit the data, the lambda CDM model with tensors called lambda CDM plus R. We get a constraint on NS. It is almost the same as before because NS is not very degenerate with tensors. And we get an interesting upper bound on tensors because Planck does not detect tensor, it only puts a limit. And here the constraint on the tensor to scalar ratio is expressed at a given pivot scale. So R is smaller than 0.12 at this pivot scale. It's not a surprise that we find no evidence for tensors, because as we said, if we look at temperature, tensors tend to suppress small scales relative to large scales. So it tends to suppress the large L's relative to the small L's. What we see with Planck is rather the opposite. You know that there is like a marginal anomaly not to be taken seriously because it's not significant. But in any case, for small L, and especially in the range between 20 and 40, the Cs of L seen with Planck are a bit lower than in the lambda CDM model. So if you add tensors, the tension will be even stronger. So it's clear that Planck does not like tensors too much with the current data release, at least, and without polarization. This constraint on R can be translated directly in a constraint on the scalar field potential during inflation, so what people call the inflation scale. And you see it's a bound of about 2 × 10⁻16 GeV to the 4. So it's a small improvement with respect to the volume up. In terms of R, the improvement is of the order of 25%, or even a bit more, 30%. It's not huge because we have only published the temperature data. With polarization, we can improve things probably much better, but we are not yet completely sure. Okay, so now this is a usual parameter space of single field slow roll inflation. Of course, if inflation is complicated, if it violates slow roll, if there are features, we cannot summarize everything in terms of the tilt and the tensor to scalar ratio. But with simple assumptions, we can. And every model of inflation will live somewhere in this 2-parameter space. Okay, so we see the constraint in the tilt centered at 0.96, and we see the constraint on the tensor to scalar ratio saturating around something like 0.12 typically. This solid line here separates the region of convex potentials and concave potentials. So let's go quickly through some typical examples. The green is a phi to the 3 potential. We don't even show the phi to the 4 potential, the quartic potential, because this is now strongly ruled out. The black is a quadratic potential, m square phi square. It is at the edge of the allowed region because it predicts a rather high tensor to scalar ratio of the order of 0.50. So I would not commit myself that this is ruled out. It is not, but it is in tension with the data. If we go in this region of a concave potential, which has a potential preferred now by the data. There are many models living there. You find, for instance, the model of the first model of inflation, Starobinsky model, with an R-square term in the gravitational Lagrangian. This model predicts a tilt close to 96 and a very small gravitational wave amplitude. So clearly this model is fitting the data very well. The Higgs inflation model of Shaposhnikov and Bezbukov and et al. Makes a similar prediction. So it's in good shape from the cosmology point of view. However, it starts to be in tension with the measurement from LHC, given the best estimate, current estimate of the Higgs boson mass connected to issues of stability of the vacuum, etc. I will not enter into details for this model. Okay, so what other concave models could we think about? Well, there is a huge family of models in which the inflaton field is simply rolling away from an unstable equilibrium point, exactly like after spontaneous symmetry breaking. These hilltop models, spontaneous symmetry breaking model, they tend to work very well, okay, because they predict a variable amount of tensor that can be tuned depending on the energy scale of the model. And they predict a concave potential, so they predict that we should be in the allowed region. Okay, so now the paper contains this very general presentation of the inflationary phase space, and then it presents a specific analysis, much more detailed, of particular classes of models, and in particular monomials models, hilltop model, which are like spontaneous symmetry breaking models, and natural inflation. Natural inflation is a model motivated by pseudo Goldstone boson, like the axion. In this case, the effective potential of the inflaton is a cosine, and the inflaton rolls away from one of the maxima of this cosine. Okay? It can be easily motivated, for instance, by axion models with loop correction and the QCD transition, etc. For these classes of models, we went one level further by using exact prediction for these models. So it means that we simulate numerically these models, integrating numerically the evolution of modes during inflation in order to get a very precise scalar and tensor spectrum. So we simulate the background and the perturbations numerically. When you study a model like this, you need to connect a given value of the field at the pivot scale to a given value of the pivot scale in wave number space. So you need to connect the values of the field during slow roll to wave numbers observed in the CMB. In order to do this connection, you must know how long inflation lasts and how efficient is reheating. And rating comes with some uncertainty because the study of rating cannot be done in a very, very precise way. So we have to marginalize over our uncertainty into reheating in order to get some definite predictions. After this marginalization, for each of these models, we compute how the chi-square of the best fitting model improves with respect to lambda CDM, and we compute the Bayes evidence factor. The Bayes evidence factor is a very good way, based on rigorous statistics, to say if a more general model is favored over a more simple model, given that on the one hand, you will probably improve the goodness of fit in the more general model, but you should be penalized for the fact that you introduce more freedom. So the Bayesian evidence answers this question in a very precise way. And the conclusion with all these models is that, of course, you improve the goodness of fit, but the price you pay in terms of added free parameter is too high. And the most natural model remains a simple model with just a power law primordial spectrum and no tensors. So none of these models is improving the Bayesian evidence ratio. So this was about inflationary model comparison with precise model. I don't enter more into detail. It constitutes one of the sections of the Planck inflation paper. The next section is about a different approach, answering a different question. in some way, it's a more conservative approach. It's the inflaton potential reconstruction inside the observable window. So what do we call the observable window? What we really test with CMB experiment are fluctuations in a given range of wave numbers. And this range can be mapped into a given range of the inflaton potential in the vicinity of the pivot scale. Okay? So we can only probe directly the inflaton potential in a small window. Then, in the previous approach, we choose an inflaton potential, assume that it holds during all inflation, and integrated the inflaton evolution until the end using the same potential. In this different approach, you rely on a given shape of the inflaton potential only inside the observable window, and you make no extrapolation outside. Because outside, after all, the potential could be very different. There could be a phase transition, inflation could be influenced by another scalar field, there could even be a short stage of inflation, followed much later by another stage of inflation. There are even good motivation for this. There are models called thermal inflation doing this. Okay, so if you try to reconstruct the inflaton potential only inside the observable window, you can try simple parametrization, because the observable window is narrow, so there is not much room for complicated functions. So you can try to tailor expand the inflaton potential at order n equal 2, 3, or 4, but only inside this window. You get a sum over quadratic, cubic, and quartic terms, but only inside this window. And then you make the following reconstruction. This plot shows the inflaton potential V of phi plotted in the vicinity of the pivot scale phi star, which does not need to be specified, in red by cutting the Taylor expansion at order 2, in blue at order 3, and in green at order 4. And you see a family of curves, and it exactly corresponds to the degeneracy that we mentioned before. We do not measure tensors, so we cannot fix V at the pivot scale. So we have a whole family of Fallot model where V can range all the way from 0 to some maximum value given by the upper bound on the tensors. And it's only if you fix V that you will get a definite shape and a definite prediction for a little piece of the inflaton potential. In all these plots, you see, it seems that there is a large density of models for large V and a small density of model for small v. So you have the impression that large V is more favored statistically than small v. This is an artifact of the priors. Here we took a prior not on V, but on the predicted tensor of a scalar ratio for these models. In fact, the prior is such that all cases are equally probable, with V ranging from very small to very large value. So we cannot say if inflation took place at nearly the gut scale or at a much lower value. Nothing forbids you to have inflation take place at 10 to the 12 GeV or smaller. Look at the green case. In the blue and red case, the scale is such that we cannot see the curvature of the spectrum. If we would zoom on each of them, we would see that they have some curvature. These pieces are not straight lines. They have some curvature. But with this scale, we cannot see this curvature. Instead, in the green curve, we give more freedom to the observable window of the inflaton potential. It can include a phi to the 4 term. In this case, because we give more freedom, we see more complicated shapes. This should not be taken seriously. It means that in this case, the freedom will be used to fit the low scale anomaly of Planck. We know that between L of 20 and 40, there is a little anomaly, not very significant, but the C's of L are a bit too low. Typically at the order of 2 sigma, so not a big deal. When we allow for this freedom in the potential, the preferred model have a non-zero tensor over scalar ratio, and they have this strange shape because on the left, the inflaton potential is not yet in slow roll, it's in fast roll, So the primordial spectrum is suppressed and you fit the anomaly. And then there is a transition to slow roll and the observable window look like in the other cases. But the chi-square in this case improves by a marginal amount. So we should not say that the green case is favored over the other cases. Now I change topic. We tried to see if features fit the CMB spectrum better. Features can be generated during inflation. Okay, then there is a long discussion. Is this natural? Is this ugly? Does it rely on complicated assumption? I will be very diplomatic because I don't know who is listening to the talk. And I think after all, it's possible to motivate features in a rather simple way. So let's take an open mind and we try to reconstruct the primordial spectrum. Okay, you have here four cases with different values of lambda. So I should explain what lambda is. Suppose that you take a complete freedom in the primordial spectrum. Then you will converge toward a spectrum that will go through the center of each schizovel, a spectrum with a lot of features that will fit all the little, in fact, it will fit the noise and the cosmic variance of the data. And it will make no sense to try to reconstruct such a spectrum. So you have to take a prior. You have to say, I impose that my primordial spectrum has features, but is smooth over a given scale in Fourier space. And this is this parameter lambda. Lambda is a penalization factor. It will penalize, in the likelihood, all the primordial spectra which have variations over scales shorter than something. So you see, in the first case, lambda is 10 to the 3. You don't penalize much. You allow the spectrum to have very short scale, high frequency fluctuation. In the last case, lambda is 10 to the 6. You have penalized small scale variations. You only allow for larger scale variations. In the last two cases, with lambda of 10 to the 5 and 10 to the 6, you see that the primordial spectrum reconstructed in each green bin, in wave number space, is compatible with 0. It means compatible with the power law spectrum. So if you kill small scale fluctuations, a power law spectrum is working extremely well. If now you allow for small scale fluctuation, these are the first two graphs, you see a feature here. You see 2 points that are above and below at more than the 1 sigma level. In this case, you have given enough freedom in the primordial spectrum to fit one of these marginal anomalies in Planck, which we don't know if they should be taken seriously or not, because they are not so significant. To be more specific, this feature is at wave number k close to 0.13 megaparsec to the -1. This maps onto the CMB mainly around L of 1800. At this scale, there is a dip in the temperature spectrum, in all the frequency bands of Planck, and especially in one of them, the 217 gigahertz. Okay, so now we are fitting, in fact, this small anomaly. But this is only in terms of sigma, it's only a 3-4 sigma improvement. You see here I'm cutting the significance of the effect in terms of sigmas. So I'm doing a frequentist approach. It's like if I would compare the delta chi-square at the best fitting values. It would be better to do Bayesian evidence comparison, but there are so many parameters in this case that it's technically impossible. So this is one approach to feature, and the result is not conclusive. We have a good fit with a given feature, but do we really need this feature? No, because the chi-square does not improve so much that we should conclude something definite. There is another approach that has been tried. In the previous approach, we bind the primordial spectrum in wave number space. We try to reconstruct it with only this prior on the scale of the fluctuations. You can try instead to fit some parametric features, meaning you assume that the features consist in a given kind of oscillation, and you fit for the parameters of your parametric features. We tried 3 things. We tried the red case, these are constant oscillation in log-log space for the primordial spectrum. It can be motivated by some models, action, monodromism. Okay. The green family of curves you see have frequency which is not constant in log of k, like in the green case. So the frequency here seems to be varying with the scale, and also the amplitude of this oscillation vary with scale. Where does this shape comes from? It can be motivated by a class of models in which you have a step in the inflaton potential. It's like a phase transition during inflation, but even with a step in a single field model. So it's one among many types of features that you could have. Just took one example because we thought maybe this example could fit the large scale anomaly at small L's. You will see if this is the case or not. We tried to fit another parametric shape with an exponential cutoff in the primordial spectrum for large wave numbers, so small values of k. And this is the blue family of curve. So we have three families of curve with respectively 3 extra parameters in the constant oscillation, 3 parameters in the green model, and 2 extra parameters in the exponential cutoff, which are the scale and the width of the cutoff. And we fit these models varying these parameters. The best fits are shown here. This is a plot of residuals. So the data points are the Planck temperature data points divided by the best fitting lambda CDM model based on a power law primordial spectrum. Okay. On the same scale and dividing by the same best fitting model, you see some green, blue, and red curves. They are the best fitting models of each of the previous 3 classes. So you can be surprised, for instance, by the fact that for the green features, here the amplitude of this oscillation seems to be a constant. And here it seems to be oscillating because the maxima of the oscillation correspond to the scale of the acoustic peaks. On the scale of the acoustic peaks, the oscillation amplitude is amplified by the physics responsible for the acoustic oscillations. This is why you have maxima and minima. What you should retain is that with a green curve, you have a freedom to fit oscillation on small L's. With the red family of parameters, you see you can try to fit some features at higher L. And with the cutoff spectrum, you can try to fit some features at low L. You know that at low L, the data see small amplitudes in temperature with respect to the best fitting lambda CDM model. But in none of these cases, I show here a plot of the delta, of the improvement of the chi-square and of the Bayesian evidence. The Bayesian evidence is, what you see here, is a logarithm of the Bayesian evidence ratio. It is close to 0. These models with features would be really significantly preferred if one of these numbers was of the order of 5 or bigger. Instead, it's of the order of 0 or 1. It means that these features provide some good fits, but the price to pay in terms of new parameters is too high, and these models are not preferred by the data. So all these complicated analyses all conclude that the power law primordial spectrum is still the best and most economic explanation. Okay, another section, the Planck inflation paper, is devoted to models with a non-canonical kinetic term in the inflaton Lagrangian. This can be motivated in many ways. It can be motivated by some classes of models like the Dirac-Born-Infeld inspired model of inflation, like the model called K-inflation. These are models coming from brain cosmology, from string theory, with this non-canonical action. More generally, all these models can be parameterized in a more general class of models, the effective theory models of inflation described by Chung and Senatore. In all these models, the non-canonical kinetic term will produce a sound speed for the inflaton perturbations smaller than 1, while for a canonical scalar field, you can easily show that the sound speed is equal to 1 in the frame co-moving with the inflaton perturbations. Okay, this sound speed has consequences. It changes the scalar spectrum because just the dynamics of the fluctuation is affected by the sound speed, of course. It changes the tensor to scalar ratio because the scalars are sensitive to the sound speed and the tensors are not. And it generates primordial non-Gaussianity. So you will see it in the CMB bispectrum, and in particular, it will produce a number FNL, which is can be defined in several ways, but these are several ways to reduce the bispectrum to a single number under different assumptions. It produces an FNL unusually large compared to single field inflation with canonical kinetic term. So the Planck paper investigates constraints on the sound speed and on the Sorrow parameter using information from the temperature data and also from the temperature bispectrum and the limits of FNL. And it's interesting that some specific classes of models, like for instance, K-inflation, can be completely ruled out because when you constrain, for instance, K-inflation, the tensor spectrum, the temperature spectrum gives you a constraint on the parameter of the model. The FNL constraint gives you another bound, and the two are incompatible with each other. So this is one of the first examples in which, by putting together information from the power spectrum and the bispectrum, the non-Gaussianity, we can start to rule out some models. At the end of the day, the analysis shows that there is absolutely no preference for a sound speed smaller than 1 and for a non-canonical kinetic term, mainly coming from the fact that, as you know, Planck is compatible with Gaussian primordial fluctuations. We are almost done. The last topic, and I think we will finish at 4 as expected, are isocurvature modes. So we know that the fluctuations seem to be adiabatic from the typical scale of the peaks, but there could be a small contribution from isocurvature modes that you could try to motivate in many different ways. The deep idea behind the adiabatic mode is that in the primordial universe, all fluctuations were generated by a single degree of freedom. The single degree of freedom could be the inflaton in single field inflation. If fluctuations are generated by 2 degrees of freedom or 2 mechanisms, for instance, 2 inflatons, or 1 inflaton, another light scalar field, the axion, the curvaton, or the inflaton and later on topological defects. There are many examples in which there are 2 independent quantities generating independent or not say completely correlated quantities generating primordial fluctuations. Then you might have isocurvature fluctuations if they are not erased by the subsequent evolution, for instance, by thermalization. So the adiabatic mode could coexist with, for instance, CDM isocurvature modes coming from fluctuations only in the cold dark matter, or neutrino isocurvature modes in which you have, for some reason, a cancellation between the neutrino density and the photon density in the early universe, or the neutrino velocity isocurvature modes, in which you have a cancellation between the primordial neutrino velocity and photon velocity. These are examples. They are not more examples. You could say, let's go to the level of neutrino anisotropic stress isocurvature mode. This cannot exist because we know that photons in the early universe are in thermal equilibrium, so they have a negligible anisotropic stress. And the total anisotropic stress in the early universe must be 0, so there cannot be other neutrino isocurvature modes. So these are the 3 known cases. The 4th known cases would be baryon isocurvature mode, but it is phenomenologically equivalent to CDM isocurvature modes. With a small fraction of this isocurvature mode, you will have an extra contribution which looks like the red, blue, or green, with typically shifted peaks. This is because you change the phase of the acoustic oscillation by changing the initial conditions in the early universe. So if you sum up adiabatic and isocurvature modes, you will have a very small shift of the peaks. If such a shift is observed, then we will have some lower bound on the isocurvature modes. It turns out that when we do the analysis, we don't have such a lower bound. So it's a bit long to explain how you parameterize these models, because you need parameters for the amplitude of isocurvature modes at different scales, because they could be tilted, and on the way in which they are correlated with adiabatic modes. It could be fully correlated, uncorrelated, or correlated with an arbitrary correlation angle. The conclusion from this analysis that I will skip because I'm getting to the end of the talk is that we tried many combinations that you can find in the paper, and in no case we have strong evidence for isocurvature mode. We can decrease the chi-square a little bit with isocurvature mode, but only by 4, while we are adding many new parameters. So isocurvature modes are not favored. This can be translated into constraint on the axion model that I don't have time to mention, and on the curvature model. Okay, my conclusions. So the paper contains a lot more information than what I said into the talk. I just tried to be concise, and since I started late, I even had to skip some slides. The final conclusion is that the simplest model of inflation, predicting just a power law primordial spectrum, and we are not seeing yet any tensors. The simplest model are the one which fits the data the best. Okay. So some people say we live in the maximally boring universe because we are not seeing new things with Planck. Some other people say we live in the maximally elegant model, since a very simple model with very few parameters can account for all the data, even when we have now much more precise data. If any of the features seen in Planck, the anomalies, have to be taken seriously, then we are neither in a boring case nor in an elegant case. Okay? But my personal opinion is that none of these features now should be taken seriously. We will see if with polarization things will change. There is a potential improvement for the next years because we will use more data in the next year. We will use polarization, and we will improve our modeling of the foregrounds, of various effects, and really we will have better data, smaller error bars. Maybe we can say something new about these features, even about the isocurvature mode, I don't know. Maybe we can exclude better some inflationary model, and we still have a chance to see the B modes. Okay? It's with a small probability, but maybe we can do that. Okay, I will stop here. All the likelihoods of Planck have been released, so you can test yourself your favored inflationary model. It's not very difficult. And this is all what I have to say today. I wish to thank Alvaro de Rújula, who lent me his computer at the last minute, since my Mac has macOS 10.5, and this seems to be incompatible with the software needed for these webinars. Thank you, and I hope I can take some questions if I understand how to do that.
Okay, Julien, thanks a lot for this very interesting talk. Thanks also for all your efforts to get a computer at the last minute. For some reason, when I speak and switch on my audio, you appear frozen on the screen. I don't know why is that. It's a mystery. But let me take questions. Please, anybody that wants to ask a question, please raise your hand, as you know how to do.
Okay, please.
I guess you can hear me. Is there any question? Okay,
I hope that somebody else than you could hear me.
So from Ifig, there is a question.
Okay, I can see friends in the list of participants, and I say hello to them. They will recognize themselves.
Hello, I have a question.
Yes.
Related to this reconstruction of the potential.
Yes.
So
I can hear you very well.
So the thing is, if I understood correctly your plot, would you have So we have some echo here. So I'll finish my question on a way. My question is, so your potential, so you try to reconstruct your potential with this method n equals 2, 3, 4, and what you find is that your field has a excursion that is order n Planck, I guess, while your potential is much smaller than n Planck. Is that correct, and how do you interpret that?
Okay, so I go back to this slide, okay, and you see that the excursion depends on the energy scale of inflation. In the limit of the lower models, in the limit V goes to 0, you see that the excursion also goes to 0. And this is a well-known Leith bound, saying that if you have inflation taking place at high energy, you have large excursions. At low energy, you have small excursions. So for David Leith, this is, I hope I interpret his thoughts correctly. This is a sign that low energy scale inflation is more natural from the particle physics point of view, because you avoid these large excursions. Okay. Now, what would be really a problem, I think, would be to have values of the inflaton potential much larger than the Planck mass. Okay, and this is not the case, of course. So then you can have discussion about how bad it is to have excursion of the order of the Planck mass, and then you are led to a discussion of high order terms in the inflaton potential, of non-renormalization terms, renormalizable terms, sorry. So depending on the people with whom you are talking, this is considered as very unnatural or very compatible with some classes of model. For instance, for Linde, it was never a problem to have chaotic inflation with a quadratic potential, with a large excursion of the inflaton field, provided that the inflaton potential itself is not above does not vary by more than the Planck mass. But in any case, what you said is only true for high energy inflation. You see that for low energy inflation, the excursion goes to 0 as expected.
Okay, thank you.
So now there is another question from Dharam. I'm giving voice to them.
Hi, Julien.
Hi, Céline.
Can you hear us?
Yes.
So, salut.
So I'm waiting for your question in Dharam. Okay, maybe you are asking something, but for sure now I could hear Céline before, and now I cannot hear anything.
I think there was probably some connection problem, just a little bit of patience. I think they're connecting everything.
Yes. I must say that Alvaro needs to take his laptop back. So maybe we can go for one quick question. I see that in Dharam.
They are writing the question on the chat.
Yeah, they are writing the question. I think it will be the last one. After, I think I will have to close. On slide 23, the people in Dharam ask about slide 23, this one. the one with P of K. This one probably. A few after. Maybe this one. Okay, so I'm getting written message from Darom, and we cannot agree on which slide I'm supposed to show. Okay, so the people in Darom will ask the question directly to me by email, I think. So if this is okay for people, I would prefer to stop now.
Okay, Julian, thanks a lot. You will not see the clapping, but there will be many people clapping to your talk.
Yes, I could see the clap. I don't know if I deserve it, but I thank you very much in any case. Bye-bye.